Alright, welcome back to our reading of categories and sheaves. These videos come out whenever they come out, whatever pace we have time for. Life's busy as a grad student. Today we're going to be looking at section 3.3 of Kashiwara and Schapira. We're going to be talking about exact functors. That's the topic of, or the title of this section. And presumably all of you who are watching this video have had a course in commutative algebra where one has met the notion of an exact sequence of modules, maybe only abelian groups, but whatever, and you've learned a whole host of functors that get applied to these objects enjoying various exactness properties. Maybe you know about localization, almost certainly you know about Hom and tensor because we've talked about those in the past, and you're sort of vaguely familiar with the properties these things have. Now in chapter 2, we learned a categorical notion of exactness, and this notion works in a very high degree of generality. We said that a sequence of maps was called exact. Well, in that case, at the level of generality of Kashiwara and Schapira, one deals with not just a single map, but with a pair of maps. And then we would look at either the equalizer or the co-equalizer of those maps, and we would declare them to be left or right exact when the next object or the previous object was isomorphic to the equalizer or co-equalizer, playing the role of the kernel or co-kernel, whatever it was supposed to be. So this was our notion of exactness in chapter 2, and now we want to talk about exact functors. So a sort of maybe naive thing is that we should call a functor exact when it plays nicely with these co-equalizers. The issue that we have here, or maybe not the issue so much as an issue for Kashiwara and Schapira, is that they want to give a very, very general definition, which would sort of be too easy. So we have to start by unpacking the following painful-looking definition. So we'll have a f of functor, c to d. No assumptions on the categories. That's sort of the point of all this, is we're trying to make this work in settings where we don't have any notions that look like the familiar homological algebra stuff. Then we'll call f right exact when the category cu, c lower u, is filtrant for any u. And then we make the dual definition. Kashiwara and Schapira do something, they say it a little bit differently, but this is equivalent. It's left exact when C upper U is filtrant. Again, for any U, I'm going to stop writing stuff that we've already written. And F is exact when it's both. That part's completely unsurprising. So, of course, in homological or commutative algebra, one learns that the utility of notions like, e.g., left exactness, is that left exact things commute with finite projective limits. Of course, dually for right exact. And one of the very first things we're going to do, maybe even the only thing we'll do in this video, we'll see how long it takes to get through all the things I want to say, is establish that this generalizes that notion by getting that property and at least showing that that's the case. But before I do that, I want to convince you that this notion of exactness is actually the correct notion of exactness. Or at least it's a good generalization. Maybe correct is a little bit too ambitious, because in order to convince you that this is truly the best definition, I would have to probably know more category theory than I do. I would need to convince you that this is somehow a very powerful and robust definition, which hopefully I'll be able to do as we go through the book. So maybe what I mean to say is that I want to convince you that this is a reasonable generalization of the exactness notion that you're familiar with. So in order to do that, I just want to show you one example, and I want to work it out in some degree of detail. So let's scroll down and make a thorough example. And the functor I want to consider is the simplest example of a tensor product. Tensoring in Z mod 2Z. And all my tensors are going to be over Z. We're going to be dealing with basically abelian groups, but because I'm tensoring them, I'm thinking of them as Z modules. But that's fine. And what I want to do is show the familiar example of this is not left exact. And once we establish some properties of this definition, it'll be very clear why it's right exact. So I won't do the right exact part, but I do want to illustrate why the tensor product is not left exact, sort of directly from the definition, and as we go, sort of explain what's happening with this notion. So first, we need to recall, hopefully you guys do remember, what the objects of C lower u and C upper u actually are. I always get them a little confused, so I have to have a quick think. But C lower u should be the one where we map in. So an object of C lower u is something like so, where F here denotes whatever the functor is in question. And then a morphism in this category is actually something slightly subtle. And this is a big part of the reason I got so confused about this notion for such a long time. Because a morphism in C lower u here, oh, actually this isn't right. But I want to show, okay, I always get these confused. It's so annoying. I want to show that tensor is not left exact. So I'm actually interested in C upper u anyway. C upper u is the category that I want. And in C upper u, I think what I wrote is correct. That an object is a pair u into some f of x by some map, which I didn't label, but I could. And then a morphism is something like this, where you get a commutative triangle of objects in whatever the target category is in this case. Well, we'll spell it all out in a second. But the important thing is that a morphism is something in Hom x, y, c such that this triangle commutes. So this is an important note, which I got confused about. So I'll put a little exclamation point over here on the side. A morphism is something which lives in C, which, if you might like, descends or passes to. Maybe passes to is a better phrase. So let's say it that way. A triangle in D. And in our specific case here, tensoring is an endofunctor. So the category in question here is Z modules or abelian groups. And this tensor functor, which I could call F, but I'm going to continue to do this until I get sick of it, is going Z mod to itself. So that's sort of one source of possible ambiguity here, is that looking at morphisms of the original objects between whatever my groups are, x and y, which happen to produce, after tensoring, a commutative triangle. So off the bat, one thing that we see here is that this is the manner in which we remember anything at all about the initial sequence. So like, everybody knows, okay, so like, let me back up for a second. Probably I've been talking now for like 5 minutes, and at least half of you are like rolling your eyes at me saying like, what the heck, Tom? Like, tensoring is not exact. How do I know that? Because I look at this baby example where I multiply by 2, and then I take residue classes mod 2. That's an exact sequence. And when I tensor, I get Z mod 2 everywhere. And this map becomes 0. And that's just obviously not exact. So that's what all of you are saying. And I agree with all of you who are rolling your eyeballs at me right now. And the point, what I'm trying to do here is show you what this has to do. What does this basic example have to say about this general definition? In other words, how do I translate this basic example into something where I can show that this example makes sense? So that's what we're going to do now. Okay, so let's fix a finitely generated abelian group. I guess I'm limiting myself to Z modules. Maybe I want to be even more restrictive than that. Although I don't think it matters. I'm just having a little mini panic attack now. Like, is what I'm going to do not going to work if they're not finitely generated? Probably it still works. I let you guys who are watching this and maybe somewhat hopefully active in reading the book correct me if I'm wrong. I fix a group G, an abelian group G. And now, in order to show that this thing is not left exact, I want to show that this category is not, since I'm doing right exact here, what I want to do is show that it's not cofiltrant. So in other words, instead of having the usual like equalizer and sort of roof-looking condition, now everything is inverted. So an object of our category then is some map that looks like this. I have an S from some G to an H tensor Z mod 2Z. And I'm going to call this guy H mod 2H. If the groups are finitely generated, then this is a perfectly reasonable thing to do, which is sort of why I had this mini panic attack, because I could take the theorem for finitely generated abelian groups and do the invariant factor decomposition, and then that together with the third, one of these isomorphism theorems, allows me to just component-wise simplify the decomposition. And all that would happen is I'd get a bunch of copies of Z mod 2Z for the free part, and the torsion part, well, if it's odd, then it would be killed because everything is a multiple of 2. And if it's even, then it just gets cut by a factor of 2. Okay, so this is an object, and modulo this concern about whether or not my notation of H mod 2H is reasonable, this is what we're going to work with. And a morphism is then, like we said, a commutative triangle. So if I stick an H1 on here, and then I can do this guy. And again, we'll call this guy H2 mod 2H2. And here, this homomorphism has to be a group homomorphism tensored against the identity map on Z mod 2Z. So in other words, it's a group homomorphism H1 to H2, which we then tensor, and after passing to this tensored object, this guy gives us a commutative triangle. Now, because I'm trying to show that this thing does not have the cofiltrant property, I get to set this up however I want to. And so what I want to do then is I get to pick my maps, I get to pick my H's, and everything is good. So what I'm going to do then is mimic as precisely as possible this baby example. So for whatever G is, I assume that G has a surjection to Z mod 2Z. And then, with this in mind, I can write something like this. Let's make it clearly a surjection. And now, for the case of with parallel morphisms, I get to pick a pair of parallel maps that go this way. And let's make them the images of 1 tensor 1 and 3 tensor 1 on Z tensor Z mod 2Z. Those descend to the same thing, so I get a nice commutative triangle. And they're obviously different maps upstairs, but both reasonable homomorphisms. Now, the important thing is that I claim that there's no way to place another object up here, x, so that x mod 2x here equalizes this diagram. How do I see that? Well, up to taking direct sums, x can only be one of a handful of things when I'm dealing with finitely generated abelian groups. And like I said, I think this story is the same in general. The important thing is that in order to equalize this diagram, if I go across the horizontal map, maybe I should get some colors. If I go across the horizontal map and then down this way, I get something which is non-zero. That means that neither of these two maps into or out of x can be 0. And that puts some pretty serious limitations on what sort of things I can pick. Because, for example, if I can't take the 0 map anywhere, then that means x cannot contain a Z mod NZ for odd n. Because then, of course, the only map that would possibly come out of that after tensoring would be 0, and we just said that's not allowed. On the other hand, if x is something else, like a z, or a Z mod NZ for even, then it can't equalize the maps times 1 and times 3 upstairs unless that map is 0. So I should write that down. No map equalizes 1 times 1 and times 3 as maps Z to Z and descends. That's not quite what I want to say. No map equalizes 1 and 3 downstairs while coming from something upstairs. Except 0, which is expressly not allowed, because otherwise you don't get a commutative, you don't get a commuting diagram. So this establishes the lack of cofiltrancy because given a pair of parallel arrows, there's no way to fit an object in there. And what is this telling us? Well, remember that a pair of parallel arrows and the object that comes before them, x is supposed to be a generalized kernel. And so if there's no generalized kernel after tensoring, then what that means is the kernel which existed previously is in some sense not compatible with this functor. In other words, that kernel is being destroyed. And so that's the sense in which the exactness condition that we're familiar with is lost. Hopefully this makes sense. I spent a lot of time thinking about this. In fact, I even put up a Stack Exchange question about this where I inquired from the great minds of the math community as to how this works. And basically the comments were all like, there's no intuition behind this. Don't bother thinking about this. Somebody gave me a very nice explanation about why I should like this object for sort of different reasons, which maybe I'll be able to get into in a few chapters. But in any case, it took me quite a while to work this out, and Stack Exchange was not particularly helpful. Okay, anyway, now that we've elaborated on this condition, now let's work on establishing these properties, and then we've already been talking for more than 15 minutes, so probably after we establish some of these basic properties, it'll be a good time to call it. Oops, sorry about that. So let's get into some general theory now. We have the proposition, the promised claim, f c to d, a functor, as always, and j will be a finite category. We'll take beta j op to c, some functor. This is, a diagram, as we're used to thinking about them. And we assume that the projective limit exists in C. Then the limit of f compose beta exists in D and is isomorphic to the image of the limit if and only if f is left exact. So this is the generalization of our commutative algebra fact, that left exact functors play nice with projective limits, and the converse is also true. Okay, so the proof of this proposition relies on a fact from section 2.4, which we didn't cover in the videos, and I'm not going to go back and do it now, but I will write down the fact because we're going to use it. And then the proof will actually be a very short calculation. So the fact is, I have, in the case of, excuse me, the fact is stated with two functors involved, but for us, the two functors are going to be the same. So we have two functors, fc to d and gc to e, and b an object in E. Then we have an isomorphism where I take the limit of the maps gx into b in CB. I realize this is a bit of a mess. I'm trying to make sure I get it right. This is isomorphic to the A's mapping to f of x, and this will be in C upper A. Got to scooch over a bit. In E, G of x, B. Okay. And I'm not going to prove this fact now. We borrow this from 2.4. And I'm sorry, I'm trying to zoom out a little bit so that everything fits, but maybe you have to pause the video and take a moment and get this. Darn, really not doing good today. Store this fact in your brain. Okay, now with this fact in mind, we do the proof of the proposition, not the fact. So we have hom in d u fx, and this is isomorphic to the limit of those z's going to x, hom d u f of z, and now we get that this is isomorphic to the limit of u mapping to f of z in C of u, C upper u, hom zx. Okay, using this quoted fact, but with this in mind, we can now do a short calculation. We have the limit over the j's. The j's, of course, are the elements of j, the argument of beta, hom d u f of beta of j, and we have a million parens. This is the limit over the j's, and now, the limit hom c z beta j, and now this is the same. Oh, sorry. No, I now need to exchange. Right, now we exchange the limit and the colimit. And we have hom c z beta j. And this is possible because we saw back in proposition 3.1 that when you have a filtrant category, namely CU, the C upper U, the category we're interested in, that you're justified in exchanging limits and colimits. I'm just a tiny bit concerned I've made a mistake with the arrows. I'm just trying to make sure that all of the variance is right. I'm a little bit spooked here. Yeah, I'm supposed to be working about projective limits. So I think all this is just backwards. This limit should be like this. And therefore, this limit, this limit should be like this. And that means this limit has to go forwards. Oh yeah, because it has to match the thing I wrote above. Ugh, terrible. And now this limit goes this way. This limit goes this way. Yeah, that makes a lot more sense. Oof. Okay, well, in any case, now this is isomorphic to the lim over z and cu. We can now just take the inner limit inside. This is the covariant argument in hom, so it goes in like so. And now we get hom, and this is now happening in D, of u f lim beta j. Okay, so the important thing now, and the upside to all of this is that we're just applying the Oneida lemma, right? Now what we've shown is that all of these homs end up the same, and the only thing that's different is since u is arbitrary, the second argument, and since u is arbitrary, the Oneida lemma tells us these represent the same thing, namely the projective limit of f of beta of j. And that's what we wanted to show.